Okay, welcome everybody to this IPROMO morning session. I would like to remind that this will not be the only session in the day, but today we will have two sessions, one in the morning and one in the afternoon, according to Rome time zone. Now it's a pleasure to introduce you Giorgio Vacchiano from the University of Milan, but he studied in the University of Turin, so we have the pleasure to cooperate in some project in forest. He will give you a lecture on climate change and mountain vegetation, and particularly forest mitigation, adaptation, and management. So please, Giorgio, the class is yours.
Thank you, Danilo. Thank you very much. Good morning, everyone. I hope you can see my slides.
Yeah.
One of the most used sentences of 2020, apparently. So the topic of the day is climate change and mountain vegetation. I am a forester by training, and I study forest ecology and management. So my presentation this morning will focus mostly on forests and their relationship with climate change, under a perspective of both mitigation and adaptation. So also management. How can we increase the mitigation and adaptation power of forests? I've seen some of the presentations that have been delivered in this school, in this course in the past few days. So I know that you have gone through the basics of the carbon cycle and the basics of climate change. Just a few numbers to remind you why it is important to talk about forests. Currently, of course, the carbon balance of the planet is actually off balance. Forgive me the pun on words. Because we are introducing an excess of 40 billion tons of CO2 into the atmosphere every year, mostly from burning fossil fuels, 90% from burning fossil fuels. And this is driving, again, off balance the carbon cycle of the planet, which would be based on a balance between emissions and sequestration by natural ecosystems. And this, of course, is driving climate change, is driving global warming, and the increase in extreme events that I know also has been a topic of this course in the past few days. So what lies ahead? The IPCC tells us different stories. I know you are also familiar with this slide already. The story that we want to avoid is a story of unabated carbon emissions, continuing undisturbed until the next century, so the end of the century, and driving possibly a global warming of +4 to +5 average temperature globally, something we really want to avoid. The story we want to live, on the other hand, is the story of the bottom, the lower line that you see on this graph. We start now to reduce our emissions. The emissions go down, go down, go down until they reach net zero at around 2050 or 2060 at most. And then they continue to go down, entering a weird territory, a weird land, which is called net negative global emissions. But what are negative emissions? How can we attain negative emissions? Well, negative emissions simply mean that we have to reabsorb more CO2 than we emit. So the flux of CO2 is actually inverted, and it goes again from the atmosphere to the ecosystems and not the other way around. So where can the carbon go? There are several pools of carbon in the Earth, in the planet. I think it's interesting to put them into perspective. The super largest pool that we have is the ocean, and especially the deep ocean, which, as you can see, doesn't even fit in this slide. If we compare the amount of carbon that each pool stores with the area of the circles that are represented here. Terrestrial ecosystems also play a role. And I think it's interesting that soils and vegetation together currently host more carbon than our atmosphere. In fact, almost 3 times as much. And this is something that has to continue. It doesn't have to change, so we don't have to take this carbon and put it back into the blue circle, into the atmosphere. And then we have our emissions, which are still apparently small, but already too big for the effects that they are causing. Forests, of course, play a big role in terrestrial carbon pools. About 1/3 of all the carbon that is stored on land is currently stored in forest, where, as you already know, it can actually go in two different places. It can be above ground, so above ground biomass, and you have a map of above ground biomass in terrestrial forests. Tropical forests stand out for the sheer amount of the living biomass that they host, that we can see. But also it can go in the soil. And there are places, in fact, in the world where the carbon stored in the soil is not only stored for a very long time, such as in northern latitudes, but also is bioamount much more than the carbon stored above ground. If we compare forest ecosystems around the world, also I know that this slide has already been projected in the past few days, we see that we basically have two different situations. One in the tropics, where above ground biomass tends to be higher than the carbon mass in the soil. And on the other hand, temperate and boreal forest, where the opposite is true. And carbon pool in the soil is much, much larger than the carbon pool above ground, which is one of the reasons why forest fires in these areas are particularly worrying for climate change, because they tend to burn through the soil and to burn carbon reserves that have been there for a very long time. Now, of course, negative emissions are attainable, something that can happen to photosynthesis. Photosynthesis is the process by which a tree takes air, basically, and turns it into wood, like this library, this bookshelf, sorry, behind me. This is actually made of air. Maybe we don't think enough about this. 1 kilogram of woody biomass, if dry, contains about half of its weight in carbon. So this is around the equivalence that we usually make. Of course, above ground biomass and soil biomass can be quite variable in the world's forests, but what we are mostly interested into are not the pools, but the fluxes. So how and where does the carbon move between one pool and another? So between the air and the forest ecosystems via photosynthesis. But this is not the only flux. We also have an opposite flux, which is respirations. All the trees need to maintain their tissue, and they maintain their tissue, their leaves, their activity via respiration. So via consuming sugars and emitting CO2, just as we do. And then there's obviously tree mortality. Some material moves from the above ground pool to maybe the litter pool or the deadwood pool, and then it can go into the soil, where it is sequestered for a longer time. Or it can be taken out of the forest as wood products. Again, the bookshelf is still a carbon pool, and I hope it will be for a very long time, because I need somewhere to put my book on. So wood products are actually one of the most important carbon pools, and are one of the way in which we can increase carbon sequestration from the atmosphere. In fact, negative emissions is something that can happen thanks to, again, natural dynamics of the ecosystem. If you take all the carbon that we have, all the CO2 that we have emitted since the start of the Industrial Revolution, we find that only half of this carbon, slightly less than half, has been staying in the atmosphere and causing global warming. The other half has been already sequestered in equal parts by oceans and by land ecosystems, our forests that we're talking about. So actually, forests and land ecosystems as a whole are sequestering between 1/4 and 1/3 of our anthropogenic CO2 emissions every year. This is an important number because it tells us two things. It tells us that forests are really important for keeping our emissions at bay, so for climate mitigation, but that they can't do everything all alone. So that they're not enough to completely mitigate, to completely compensate our emissions, especially they will continue to build up. Now, the carbon that is sequestered into forest ecosystems doesn't stay there forever. One important dynamic that is studied today in forest and climate science is the concept of carbon turnover. So how long does an atom of carbon that has entered the ecosystem stay there? How long does it stay there because before it is expelled again, or it is respired, or it is emitted again into the atmosphere? So the ecosystems that store carbon for a longer time, on average, are of course the ones that help us most, because they help us buying some time with sequestering carbon and keeping it there for some decades. So you can see here the carbon turnover time of some ecosystems, even non-forested ecosystems such as tundra, which actually has the longest carbon turnover time. Why is that? Because the climate is cold, so degradation and mineralization of organic matter is slow, and carbon stays there for a longer time. Again, this is why it's very important to preserve tundra, to avoid as much as possible catastrophic fires in the tundra, so to keep the carbon there for the longest time possible. On the other hand, tropical forests, so the ones that grow in warm and moist climates, are the ones where carbon turnover is the fastest. It's really rapid to mineralize organic matter there, and so carbon doesn't stay there for a long time. But this is not a good reason to remove them. As you know, currently the global trend is still a deforestation trend. So the forests in the world are still decreasing, even if at a slowing rate, at least for the last decade. But of course, when we remove forest cover for good and replace it with agricultural crops, for example, or pasture, the carbon that had been stored in the trees, had been sequestered in the trees, and eventually also in the soil, ends up in the atmosphere again. So currently, deforestation is responsible for about 3 gigatons, 3 billion tons of CO2 every year, which is about 1/10 of our global carbon emissions right now. Of course, as you may already know, not all the deforestation happens because of the responsibility of the country where it happens. But again, between 30 and 40% of it is made to produce goods that are then traded internationally. So sold and bought by countries overseas, including Europe and including Italy, of course, which is then responsible for something called embedded deforestations in the imported goods. I will come back to this point later on. Another source of emissions of carbon from land ecosystems are fires, forest fires, land fires. We know that some fires are natural, a part of the natural cycle. Some are man-made, or at least they are ignited by men, both on purpose and in a non-voluntary way. But all fires in the world are under danger of increasing their impacts due to climate change, and due to the increase of drought, of global temperatures that dry out the vegetation and made it more prone to fire spread, which is the most important phenomenon. Once a flame is ignited, the really important thing is whether it will spread or not. That determines whether the fire will do damage, will put human life and activities under threat, and how much emissions it will be responsible for. So currently, fire emissions globally are really, really high, in excess of 7 billion tons of CO2 per year. Again, some of these are natural, so are part of the natural carbon cycles, but some are not. Because, as I said, fires are increasing under climate change. And so this creates a very dangerous feedback, a negative feedback between climate change and fire emissions. That fire emissions increase the concentration of CO2 in the atmosphere, which again make drought and fires ever more likely. The union of deforestation, drought-induced forest mortality, and fires means that the function of carbon sinks by our forest is declining. There are recent research published this year on the journal Nature that show that, for example, the Amazon basin is forecasted to stop serving as a carbon sink in 10 years from now, by 2030, because of ongoing deforestation, because of increasing mortality and fires. So more trees will die and will emit their carbon back into the atmosphere than trees that are growing and absorbing that carbon back. So for other basins, the Congo Basin in Africa, for example, the sink function is a little more stable, but still it's starting to decrease. So we really have to invert this trend, because we cannot afford an Amazon basin becoming a carbon sink, becoming a carbon source, and then eventually experiencing increasing degradation and maybe overcoming its tipping point. At the global level, forests are still a carbon sink. They sequester about 4 billion gigatons CO2 per year, which is excluding deforestation and fire. So if we include the effects of deforestation and fire, this figure decreases by about half. The situation is very different across the world. So the colored bars here represent the net forest carbon flux, and also what happens with deforestation in orange, and with forest growth after deforestation happens, which in some places can be not a very good, but a good replacement for the previous forest. Again, we have to see whether the sink function of the forest is increasing or is decreasing through time, whether we can expect the forest to continue to serve as a carbon sink or not. This is the big question. One of the most talked about mitigation options, plant mitigation options, is tree planting. So if forests are still a carbon sink, why don't we extend them? Why don't we plant trees where we can? And there was one study, one publication on journal Science last year, 2019, that tried to estimate the globally available area to plant new trees using remote sensing and advanced analysis techniques. So the yellow area that is flashing in and out of the picture is supposedly the area that is available for tree planting. The study concluded about 1,000 billion trees, so 1 trillion trees, can be planted actually in the world. And supposedly, when they mature, when they grow, this would be able to sequester an excess of 700 billion tons of CO2, which is 2/3 of all the emissions that we have produced in our history. Now, these figures have been heavily criticized for a number of reasons, and are for sure overestimates. For one, a lot of the yellow areas that are flashing now, especially in Africa or Australia, are in savannas. There are a lot of good reasons for not planting trees in savannas, the most important of which being that we want savannas to be savannas, not to become forests, because they host biodiversity, they have some relationship with us that is good like it is, and we don't want them to turn into a different ecosystem. Also, carbon estimates have been criticized for being overstated, mostly because the untold assumption is that ecosystems without trees currently host 0 carbon, which of course is not the case. We have seen that carbon in the soil, even in steppes, in tundra, in savanna, can be even higher than carbon in above ground biomass. So again, this has led into an unfortunate overestimate for this study. But there's also another reason for not planting trees everywhere we can. In some places, the net climate effect of tree planting can even be a negative one. So trees do not affect climate only by sucking in carbon. They also have an effect on what is called albedo. So the power, the capability of land surface to reflect or absorb heat radiation coming from the sun. In a lot of places, especially in northern latitudes, a snow-covered ground has a greater ability to reflect sunlight, so a greater albedo, as opposed to a forested ground, so a snowless ground, which is darker in color, And as you enter, it's like when you enter a dark car or a blue car in a hot summer day, you immediately feel the heat. So the land, the forested land, would feel more heat in this case, and that would lead to a net negative climate effect. So possibly the best region to focus our tree planting efforts are the tropical forests, both because they are the ones that are being degraded and deforested the most and the quickest, and because the albedo change would be positive in this case, because the dark tropical soil would be even darker if it were not for the trees on it. So different things to take into account if we want to compute the overall effects of trees and tree planting on our climate and our temperature. And in fact, there's not only tree planting. This study on the journal PNAS in 2017 outlined 20 different nature-based solutions to mitigate climate change, and also tried to assess their effectiveness in terms of billions of tons of carbon that they can sequester every year, and also their cost. So the dark part of the bars that you see here is the low cost proportion for each of these measures. And you see reforestation, so tree planting, has the greatest efficacy, the greatest efficiency, the greatest amount of tons of carbon it can sequester, but it is also one of the most expensive measures. It doesn't have a low cost portion. As opposed, for example, to avoided forest conversion, so avoided deforestation, improved forest management, which I will talk about in a few minutes, and also different measures in terms of improving agriculture, improving rice cultivation, improving grazing and pasture, preserving wetlands, a lot of different measures. Now, if you put all these together, both the cheap and expensive part, estimates are that these can provide about 30% of the climate mitigations that we would have to carry out if we carried on increasing our emissions. So again, strong message here. We have to reduce emissions first. Otherwise, even with all the nature-based climate solutions that we can deploy, the land ecosystems will just not be enough, not be powerful and spread and in good health enough to take care of all our emissions. In fact, even less than half of our emissions. And I've taken an example from Italy here, from the National Emission Report of 2019. Currently, the CO2 emissions, the CO2 equivalent emissions of Italy are between 350 and 400 million tons of CO2. That's the last line. Of course, they have declined through time. They have been reduced, which is good, but not enough yet. The proportion sequestered forest and land ecosystems, which is under the line LULUCF, Land Use and Land Use Change in Forestry, is about, you see, between 5 and 10% of this. So between 5 and 10% of carbon emissions in Italy are currently dealt with and absorbed by forest and land ecosystem, which is not much, especially in years like 2017, which is the last in the table here, which was a very bad year for forest fires, maybe the second worst year for forest fires since 1970. And as you see, the amount of carbon, the net sequestration in that year by land use change and forestry was half than the previous year, because a lot of carbon came back into the atmosphere due to the forest fires. And this again shows a breakdown of the CO2 fluxes in the LULUCF sector in Italy across time. You see in the positive part, carbon emissions, in the negative part, carbon sinks. So the carbon sink is basically or almost exclusively carried out by forests. And again, in the severe forest fire years, so the peaks in the red dashed line, you see that the forest carbon sinks also decreases. It tends to zero and then comes back to be a negative sink in the next year. So forest fires are really, really driving currently the percent of emissions that Italian forests can sequester every year. Now, forests, of course, can be used to mitigate climate change, but there is one caveat. They're doing a lot of things by themselves, and we are not allowed to be entitled to carbon sequestration by natural ecosystem dynamics. That is something that already happens. We're not doing anything to improve it or to let it happen. So the nationally determined contributions to the Paris Agreement can account only for anthropogenic changes in carbon sequestration. So we can account only what depends on us. And this is why currently the NDC of the European Union has actually a very, very small amount that is depending on LULUCF, on changes in forest and land use. Of course, that can do a lot about deforestation, like Brazil, Indonesia, and Russia, have a larger share or a very large share of their NDC, which relates to the LULUCF sector, which is basically would be stopping or avoiding deforestation. Planting trees also has other drawbacks. The first one is time. It takes time for a tree to grow, and we don't have that. We don't have the time. We have to start mitigating climate change now. So that's the first drawback. The second drawback is that planting trees is not does not automatically mean that they will become a functional forest. It's still an artificial ecosystem, especially in the first years. It's very vulnerable to drought, to weather extremes, to forest fires, for example. All people in the world that are currently talking about planting millions or billions of trees, it would be much better if they change their message. We don't want trees to be planted. We want trees to be planted and grow and become adult trees, functional trees. So just remember, planting is not enough. Even from an economic standpoint, you usually have to invest resources or even more resources in maintaining your plantation in the few years following the time of planting. So actually, this means that we have two main ways of using forest for climate mitigation. One is increasing carbon stocks through afforestation, through doing less harvest if we can afford that. The other one is to avoid carbon losses, so avoid deforestation. As you can see in the graph, the concept, again, is to calculate differences relative to a baseline. So we take what would happen without any action, then we take the consequences of our actions, and we take the difference in terms of carbon. This is the carbon that we are entitled to account as effective climate mitigation and to put in the NDC for Paris or in a voluntary carbon market scheme or whatever. This is also the same logic that currently regulates LULUCF accounting in the European Union. We have a new directive since 2018 that tells us how to account the carbon that is stored or is sequestered by our land ecosystems in Europe. And what we have is something called a reference level. The reference level is the way in which we think our forest will develop in the accounting period. So let's say in the decade between 2020 and 2030. That's the baseline. Whatever will happen relative to this baseline will determine whether we accumulate a carbon credit, if we manage to increase the sink somehow relative to this baseline, or a carbon debit. We decide that we have to increase harvest for other reasons, or if we have man-made disturbances or even deforestation that decrease the sink. Another important point of the LULUCF regulation is that these carbon credits can, of course, be used to offset debits in other sectors, for example, in the energy or the transport sector, but only up to a certain point. And this point, this cap, is really, really low. So for example, for Italy, the cap is 11 million tons in 10 years. So about 1 million tons per year of CO2 we can move from the forest credit and compensate debits in other sectors. But this is a very small fraction of the net sink of the forest. It's less than 10%. of the net sink of forests that we have. So, and this is a good measure because it prevents us from carrying out with excessive emissions in other sector because, oh, well, we have forests, they can cope with it. No, they cannot cope with it. So there is this cap. Whatever exceeds this cap currently is available or will be available when we will have the rules for trading on voluntary carbon markets. So forest owners, forest managers can quantify the benefits in terms of carbon that follows some action in improving forest management, and they can sell and value these benefits on the market and sell them to whoever wants to buy them. Firms, citizens wanting to compensate their private emissions and whatnot. There is a periodic report globally on voluntary carbon markets that helps us assess the situation. Of course, there are several actions that can originate voluntary carbon credits. Forestry is only one of them, but it is the one that usually earns the highest prices per ton of carbon. So it's an interesting opportunity for forest managers and forest owners to try and value the effect of their management in terms of increasing carbon sequestration. One weak point of voluntary carbon markets currently is that the trade almost always happen overseas. So buyers in one country, in most cases, buy carbon credits that are generated in a different continent. You see the hotspots of generating carbon credits currently are East Asia and Africa. The most frequent buyers are based in Europe. This is not particularly effective because it detaches the buyers from the sellers. So it doesn't generate attachment to land. It doesn't generate interest in what actually is made on the land to generate these carbon credits. So it would be to improve carbon generation schemes and go for local trading schemes. Ones where the buyers can actually see the forest where carbon generation is happening, and they can be more attached to the land, more attached to conservation or improved forest management. And again, I will stress this point once more. In order to generate a certified carbon credits, you need to meet these three criteria. The first one is additionality. So what we have just talked about, you have to take your baseline to whatever would happen in the absence of action, and then only take the difference between that and the consequences of your action. The second criteria is permanence, which does not mean forever. So most of the rule books for certification of carbon credits now talk about 20 to 30 years of permanence. So you have to commit to keep your carbon in your pools for 20 or 30 years. And then, of course, voluntarity. You cannot be paid for whatever nature already does on its own, or for government-led schemes or things that fall under international agreements such as RED, or again, whatever will happen with the Paris Agreement. Now, we are talking about climate mitigation by forest. Actually, however, forests provide us with many different ecosystem services. There are provision ecosystem services, food, products, building material, regulation ecosystem services, which are not only carbon sequestration, but also soil and slope protection, water regulation and water provision. Also very important cultural services in many places of the world, landscape, recreation, spiritual or cultural values. And especially in densely populated countries, such as Italy, where I live, or Europe, people actually ask many things at the same time to the same forest. They ask these trees to act as carbon sinks, to provide wood at the same time. So you see there are obvious trade-offs here, to protect the soil and to protect themselves from natural hazards, to host biodiversity and to serve as habitat for endangered species of flora and fauna. So one forest has many services, many benefits at the same time. This, of course, provides challenge because we can focus only on carbon. So what's best for carbon maybe it's not good, or it's not the best option to provide these other services. And this is at the heart of sustainable forest management. So sustainable forest management is the group of sciences and techniques that try to maximize the provision of all desired ecosystem services from a forest while keeping them intact for future generations. So that's the origin of the word sustainable. We want some benefit from the forest, but we cannot deplete them for the future people to come. And what is the key phase of sustainable forest management? What is needed to do sustainable forest management? Planning. We have to plan ahead. You cannot go into the forest and manage on the spot or once every long while, because you wouldn't have an understanding and a feeling for the overall effect of whatever you're doing. Forests are growing slowly. They take a long time to develop, and we have to adopt a forward-looking perspective, looking ahead maybe 30 or 50 years. And that's the reason for making a very good plan in advance. Making a plan means deciding what's the vocation of each forest. What do we want it to do? Do we want it to be a productive forest? Do we want it to preserve it for biodiversity? Or do we want to increase or do we want to increase carbon sink and so on? So zonation, distribution of the different functions of the forest, and plan ahead to forecast how much it will grow and then how much we can harvest as a consequence without depleting all the other ecosystem services. And the other great tool that's helping sustainable forest management nowadays is remote sensing. Remote sensing has been around for a while, but is becoming ever more accurate. Since last year, for example, just one example here, NASA has launched a new satellite with a new sensor, which is called Jedi, such as in Star Wars. And Jedi is an orbiting radar. So it's an active sensor. It sends down radar pulses, and it reads how they are bouncing back from the surface, and it interprets what's on the surface based on how many impulses are bouncing back, and how they are bouncing back. So this is an example of a reconstruction of a forest canopy in the eastern United States as seen by this orbiting radar satellite. The resolution is 25 meters on the ground, so maybe not very fine, but we can have an idea of forest structure and also forest growth if we go over it again through time for very large areas, which is convenient. And these are all also freely available data. Everything is made available for free on the internet. So we have to adopt, with all these tools and with these bases, a climate-smart forestry. What is a climate-smart forestry? Is a forest management that acknowledges the synergies that exist between climate mitigation needs, so improving the sinks, avoiding losses, and all the other ecosystem services, which we shall not forget. And it optimizes the efficacy and efficiency of forest contributions to climate mitigation, taking into account not only carbon, but also other biophysical effects, such as albedo, as we said before. But also other effects. Climate-smart forestry, in fact, must adopt a comprehensive, a larger perspective, just not the trees in the forest, because that's not the end of the story. Wood products, you remember, I told you they are an important carbon sink. When the wood is taken out of the forest, it can keep on sequestering carbon inside it for a long time. And this originates products and materials that can be powerful for climate mitigation because they can allow us to replace other things that are more negative in terms of their impact. There's a lot of talk about bioenergy from wood. People say if we burn wood instead of oil, instead of coal, instead of natural gas, we are actually saving some emissions because the CO2 that is emitted into the air actually goes back into regrowing trees if we are careful enough to grow back trees where we harvested them to take the wood that we burn. Now, this is a not perfectly correct view for a couple of reasons. This is the last topic before the break. So is burning wood really climate neutral? Of course, this is what happens really in the carbon pools when we burn wood. So the carbon is held in the forest, in the trees, on the left side of the graph here. Then we harvest it, so it decreases in the forest, and we burn it immediately or after a short while. So actually, we have some carbon that goes back into the atmosphere. And then, if we were careful enough and skilled enough, the forest that we harvested grows back. It takes some time to grow back. Time originates what is called a carbon debit. It's like the extinction debit. So we are indebted towards the forest in terms of carbon. And so the net effect of burning wood as compared to burning fossil fuels is compensated only when the carbon debt is repaid. So when the forest actually grows back. And this determines everything, determines the actual outcome of the choice. Forests that are quick in growing back and that don't lose a lot of carbon when harvested are better. Forests that grow very slowly and have a carbon back repayment time that is really, really long are not helping, so are not good for being harvested for burning. Super fast growing forest or tree plantations, so even outside natural forests, are good because they have a carbon back debt payback time which is very short. Burning wood is not the only options that we have to generate electricity. So one message that I would really like to stress, if we are to calculate the carbon benefit of anything, the key is to know the alternative. So what is the alternative in this case? Is it burning fossil fuels? Okay. Or is it maybe using some other renewable energy sources, which actually can be even cheaper also, as you see from this graph? Well, maybe in that case, the best use of wood is obviously not to burn it. But in fact, to use it, if we can, in materials, in long-lived products, where it can replace not energy-producing materials and sources, but it can replace cement, it can replace steel, it can replace plastic in many ways. And these are all materials that are heavily carbon intensive. If cement was a country, it would be in the third place for carbon emissions globally. 5% of overall emissions actually comes from cement in the world. So starting to use wood or continuing or resuming to use wood in our house building is a key also to climate mitigation. And according to some study, it could bring European carbon sinks from forest from 10% to 20%, because we would have to account also all the carbon that would be stored in these kind of products. Just to give you a magnitude, if we replace 1 cubic meter of concrete with 1 cubic meter of timber, we are saving 1 ton of CO2 from avoided emissions. Of course, the key here is to harvest that timber sustainably, as we said before, not from areas at risk of deforestation, not from one spot, one-off interventions that are not planned. And globally, there was one study last year that tried to quantify these substitution effects of wood. So how many emissions, CO2 emissions, we can save from both fossil fuels and materials by using wood instead of them. It's interesting because different countries have very different potentials, but there are in fact countries where sustainably harvested wood can play a role in national carbon mitigation by forest. Again, if harvested sustainably. What is recommended is to use the so-called cascading use of wood. This is what the European Forest Strategy is recommending since already several years. So long-lived products are the ones that keep carbon for the longest time, and the ones to prefer. The leftover from the processing of these products and from the wood chain, the part of wood that doesn't or cannot have any other use, then it makes sense to use it for burning, to produce energy instead of using fossil fuels. So use of wood, and we're not very good currently in making these happen. So a lot of wood is still taken and burned right away, which is not consistent with this approach. Last question: how to quantify is if harvest is sustainable? Well, the most basic fact, of course, there are several criteria for sustainable forest management, but the most basic one is that harvest must be lower than yearly forest growth. So every year, the forest and the trees grow, they produce more wood, new wood. If we take less than that every year, they know that the forest will stay there, and in fact, it will even increase. It's interesting to compare, to use Italy as an example, because currently, even if the data is not very good on this, we think that we are harvesting between 1/4 and 1/3 of the annual forest growth, which seems really, really sustainable. So the forest is growing, and in fact, the forests are growing in Europe and in Italy. Italy is among the top 10 countries for forest growth speed for natural processes. So instead of deforestation, in Europe we have natural afforestation. 800,000 new hectares every year of new forests are growing on marginal lands that are abandoned from agriculture, from pasture. People are not interested in cultivating there anymore. They're going to the cities, and the forest is free to come back. It seems really, really a sustainable choice and a good idea. We harvest less than it grows, the forest expands. But that's not the whole story. There's a dark side to this story. And the dark side is that, taking Italy again as a country, as an example, we have a much higher demand of wood than we can satisfy by harvest, or that we actually satisfy by harvest. So if you look at the import bars here in this graph, 80% of the wood that we use is imported from abroad, even if our forests are expanding. So what we are doing is not saving the forests globally, it's just delocalizing our impact. Where? Well, we are commercial partners of countries such as Romania, such as Paraguay, such as Cameroon, countries that do not have very good regulations on forest use and forest. So in fact, what happens is that about the same amount of forest that grows naturally in Italy every year disappears abroad because of our imports. So this is the embedded deforestation. And now I'm not considering only wood, of course, which is only the start of the deforestation chain in many countries, but I'm especially considering also agricultural products, soybeans, meat, leather, palm oil. So this is an important thing to know, one that the European Union is starting to do something about, and possibly, hopefully in the European Green Deal, the upcoming regulation that comes next will be one that stops or limits severely this embedded deforestation. So stops importing products or make it really difficult to import products that are responsible for deforestation abroad. But this is just an example on how things are connected between climate mitigation, between forest and wood use globally. So we cannot just look at one country. We have to assess the effects that it has on the global scale. This is the end of the first part of the lesson. I know that usually there is a break now, maybe questions. So I asked Danilo if there has been any questions collected.
Okay, now, thank you, Giorgio. Thank you very much for your very interesting presentation. And if there are any questions, please, now it's the time. Nobody wrote in the chat, but I guess they are trying to digest all the information you provided. So please don't be shy. As foresters, we are friendly, so
Very much so. Maybe we can take a break to think about what has been said. I hope it was clear enough. I hope there are no questions that is not that I wasn't clear. But if that was the case, please speak up or write up and ask me to repeat some ideas or concepts.
Okay, if you agree, okay, there are very good information. This is the first feedback from the class.
Thank you for the feedback.
We can stop now for 5 minutes, and we can continue after this break. So see you in 5.
Asking actually 2 questions. One was relative to the conversion of forest to pastures and meadows in Trentino, in northeastern Italy, under the goal of restoring or preserving traditional landscapes. Of course, pastures store a little, or actually pastures can absorb a little less carbon than forest, but not too much less. So actually they can be quite competitive in terms of carbon sink. Also because when you count the overall carbon sink effect of a forest, you have to take into consideration the risk of losing above ground carbon due, for example, to natural disturbances or climate-induced extreme events, such as the Vaia storm that hit precisely those areas a couple of years ago. So my opinion is that, as I said, we ask several things from terrestrial landscapes. We don't ask only carbon sequestration. So if there is a comprehensive strategy for climate mitigation, for the key is to know that, okay, we will convert this part to pastures, so we're losing a bit of sink capacity, and we have to gain it back, to make for it somewhere else or in other sectors. So the key is to have a comprehensive strategy for all the territory, maybe all the province in this case. The second question, if I know studies which try to evaluate economically the regulating services of forests, there are some. The easiest ones are the ones that try to give a value to carbon sink, to climate mitigation. One way to do that would be to use the social cost of carbon, which is an economic estimate of the economic damages that each ton of CO2 does when it goes into the atmosphere. The almost easy ones are also those that deal with direct protection from natural hazards, so protections of cities or roads from rockfall or landslides, because you can economically estimate the avoided damage, or maybe the avoided cost of protective infrastructure that you don't have to build if the forest is playing that role. Much more difficult, or according to someone impossible or unwise, is to assess the economic value of the habitat function, so the biodiversity that is hosted by a forest. It's very hard to assess that, and some think that it is also unwise because we shouldn't attach economic value to biodiversity, because no matter how high the value would be, it would still be finite. So it would generate the danger of justifying removing that biodiversity if higher economic gains are to be attained. In Italy, we have called the Natural Capital National Accounting. There are 3 yearly reports which have been made by ISPRA, our National Environmental Agency, on the value of natural capital and natural ecosystem services in Italy. And if I remember correctly, in the second report or third report, I'm not sure, there is an economic estimate of all the ecosystem services provided by forests in the country. So the website of ISPRA in Italy, Natural Capital Report, and you will find methods and results for this kind of evaluation.
Okay, thank you, Giorgio.
I will see if I can find the link.
There is another question from Zana, and will be the only one because we have to start again. But please, if you can answer it, I'll read. Would like to know Giorgio's opinion on moving plants uphill due to climate change. And does remote sensing detect just surfaces covered with forests or even one covered, for example, with shrubs? I'm wondering now if all these percentages are accurate, since forest primary production is not the same as surface covered with shrubs or grassland.
Okay, these are actually two questions, I think. So regarding forests that move or are moved upwards in response to climate change, I will address this topic in the next hour. So I hopefully can answer this question as I talk. I'm not sure I understand correctly the second part of the question. So it deals with whether remote sensing devices can actually see everything that there is in a forest, including the understory, including shrubs and herbs. So whether the carbon estimates of the flux in the forest can be underestimated because we're not seeing a part of them. So if this was the question, then I would say that the estimates of carbon fluxes by forest are not only made by satellite. They are made, actually, they can be made by in three different ways. Oh, sorry, I don't have the video on. I just now noticed. Might be helpful for answering. There are actually three different ways in which we can measure carbon fluxes in the forest. One is by remote sensing, but in fact it's the least accurate one for the very reason that Zana, I believe, is saying. So we cannot see everything in a forest just with a satellite. And also because we're not measuring carbon fluxes directly. We're only measuring some proxies, some indicator variables, such as the intensity of photosynthesis, the health or the biomass of the forest, or the height of the trees. And so these are all proxies that need then to be calibrated with some more detailed measures. The other two ways, one is very analogic, is just to go to the forest once, measure everything on the ground, and then go back a second time 10 years later. So this is called forest inventory or forest survey. A lot of countries, fortunately, have forest inventory programs once every 10 years or 15 years, or on a permanent basis, rotating the parts of the country that are subject to inventorying. And these are, in fact, the most reliable information that we have on carbon fluxes. Because then, if you have your boots on the ground, you can measure not only trees, but also grasses, shrubs, soil, and so on. There is a third way, which is by in a direct way, measuring gas exchanges in real time as they happen. And this is called the Eddy covariance method. It's based on basically infrared sensors that are able to see the amount of gases that are going up or down above the canopy, above the top of the forest. This is quite interesting because if you want to reach above the top of the forest, you have to build a very tall tower. So there is a network globally of these Eddy covariance towers. There are, I think, about 800 of them that measure constantly the intensity of gas exchanges in and out on the forest. But these also need to be calibrated. Of course, this CO2 is the result of the photosynthesis. All the living beings that are in the forest, or the respiration on all the living beings, but the measures, when we compare them to the inventory, they don't match. As often happens in science, if you measure something by two very different techniques, you have two very different answers. So there are a lot of research in trying to understand the reason for this mismatch, which can vary from different places to different places. But these are the three methods, and if they are used in combination, especially, they can provide us with pretty accurate estimates of the carbon fluxes globally. I hope I have answered the question.
Okay, Giorgio, thank you very much. Now we can start again with your lecture. So please, if you wanna share your screen, because now it's completely white.
have a bit of a slow response on the side of my computer. Just give me 1 more minute.
No problem. Okay, and while you are trying to fix it, Zana is thank you for your
yes, now I see.
answer.
Thank you. Good. So I think you can see a white background. Or if you do, we can resume the slideshow. Okay, the second part of my lesson is what happens the other way around. I have talked about climate mitigation using trees, forest, and wood. I would now like to focus on the opposite effect. So whatever climate change does to the forest, to the trees, and also to their action as carbon sinks. So here again, we start from something that we shall never forget: the intensity of our climate change inducing emissions at the moment. It is soaring and going above 40 billion tons of CO2 every year. But this generates not only warming. On the left side, you have the temperature increase in the last decades, but also generates an increase in the frequency and severity of extreme events or climate-related events. Droughts, floods, extreme rainfall, heat waves, storms, hurricanes. These all have a very strong and very fast impact on forests. So we should not only think of the climate change impact on forests just as some gradual process happening through a temperature.
Giorgio, we lost the communication. I guess there are some connection issues concerning Giorgio's, and while he's trying to fix it, we would like to make a short announcement. I would like to remind you that all the presentations are recorded in the platform, and I send you by email, and all the videos are downloadable, so you can download them, so you can keep them for the future. And you don't have to mind to ask for an expiry time.
And,
okay, Giorgio.
No, that's Rosa Laura. Hi, good morning, everyone. While we wait for Giorgio to connect again, I would like to add to what Danilo was saying, is that we would encourage you to share these presentations with your colleagues and other people interested in the topic. We want to reach out to... Okay, I think Giorgio is connecting again.
Thank you, Rosa Laura. Thank you, Giorgio. We missed the last, let's say, 3 minutes of
Okay, sorry.
speech.
Yeah, I noticed
No problem.
I had a problem. I was talking to no one. But thank you, Rosa Laura, and hello, by the way. So I think I should resume from maybe?
Yeah.
Okay. Yeah, Danilo, please, if there are problems with the connection, please highlight the chat so I can stop talking basically and wait for the connection to come back. Thank you.
Yeah, maybe you can switch off your webcam. So just to
Yeah, let's try to save some bandwidth. Can you hear me okay?
Yes, please.
Okay. Okay, so as I was saying, the effects of climate change on trees are manifold. There is the increase in temperature, which is gradual, but also the increase in the severity and extent and frequency of extreme events. I will talk about this in a minute. First, I would like to focus on another effect that is often forgot. We know that the reason for climate change is the increase in the concentrations of CO2 in the atmosphere, something that we are putting there. But we also know that trees like CO2. They eat CO2 for a living. It's their food. So we may think that increasing CO2, something that's called CO2 fertilization, can improve tree growth, can improve forest growth and performance. And in fact, some study using simulation models of forest growth some years ago showed that if we also take into account the increasing CO2 concentrations, the response of forests to climate change can shift from negative to positive. So all the red dots and yellow dots that you see on the right, that is the forest that will respond negatively. So forests express a positive response thanks to increasing CO2. But again, however, this is not the whole story. More recent research, and this is a very active field of research, it's really, really interesting, at least for me. The question on how long will sustained photosynthesis, will CO2 fertilization, how long it will last. Maybe the trees will hit a rooftop, will hit a maximum cap of photosynthesis, and they can't do more, even if CO2 is increasing. One reason that will limit the carbon sink, even in the presence of CO2 fertilization, is one of the few laws that we can find in global forest. And the law is this: live fast, die young. Globally, it was found that the trees and tree species that live faster, that is, the ones that express the higher growth in the initial years of their life, they also have a shorter life, a much shorter life. Think about a poplar, think about a willow. They can put up a very significant growth in the first years, but they have a very limited, a very short longevity. Maybe 100 years, they become old and they die. So with CO2 fertilization, we are boosting tree growth. We are making trees eat more and we are making them grow faster. But this will happen at the expense of the length of their life. So overall, the carbon effect will be negative because the trees will live less long and they will store carbon for a shorter time, putting it back into the atmosphere sooner. Another limitation to this, and this is also a very much debated issue, is the effect of forest age, or tree age and forest age, which are two very different things, on the carbon sink. And this, again, for example, is with those towers that I was explaining before. So we witness the real-time gas exchange between the forest ecosystem and the atmosphere, and we put it in relation to the age of the forest. Now, the results are quite contradictory if you take many studies, but currently the best evidence we have is that the carbon sink reaches its maximum at an age between 50 and 150 years. And then it starts slowly declining. It's still positive, so it means old forests and very old forests still are a carbon sink, but a decreased one. They tend towards equilibrium. They tend toward zero net exchange of gas. Of course, this is not a reason for getting rid of old forests and replacing them with more effective, young and brilliant forests. Because old forests, or old growth forests as they are known, have a lot of other advantages that we want to have. They are treasure troves or biodiversity. They host hundreds and thousands of species. They actually are a carbon storage, a safe. So they don't sequester at a very high rate, but they already have a lot of them. So we don't want to lose it, and so on. But in some places of the world, these data can be useful in devising climate-smart forest strategies. So maybe shortening some rotations in order to attain the fastest sink possible. A third limitation to the response of trees to the increase of CO2 is water. So trees are just like us. In order to live, in order to do their thing, they need to drink. If they cannot drink because water is not there, they cannot do photosynthesis, even if there's a lot of CO2 in the air. A very nice picture of the limiting factor for forest growth globally. And you see all the red and purple areas in the graph are actually limited mostly by water. So these are the places where CO2 fertilization would not be effective because climate change would bring about less water and so limit forest growth much more. What happens when the trees cannot drink, when the forest cannot drink? This is a satellite analysis of the evaporative stress in some Costa Rican forestry in February 2019, so last year. This was, I think, under an El Nino episode, if I remember correctly. So a heavy drought, water stress. There is forest there, but it is put under immense stress. The increased heat from the air asks for a lot of water, makes a lot of water evaporate from the soil and from the tree. And after a short while, this water can run short. And in fact, climate change is increasing droughts and heat waves globally. This is a study that tried to map all the episodes of drought-induced mortality and decline in global forests. And as you see, these are spread globally in all biomes of the world. Also, they can include a vast number of species. So not only monospecific forests are at risk, as most people think, but also very diverse forests. You see again in Central America, for example, an episode of almost 200 species of mortality happened and was monitored. So this is really a global phenomenon. Now, what happens actually when a tree runs out of water or runs short of water? Well, two things happen. One is that trees try to protect themselves. They try to save their water if there's little available. So how do they do it? So if you were a tree, the best way to save water is losing it. And trees lose water from their leaf due to evaporation and evapotranspiration. So a way to save water is to shut down the leaf, to temporarily close the stomata, which are the pores where the gas goes through. If you close the stomata, and a lot of species are able to do that, then you are preventing water loss. But you are also preventing photosynthesis because gases cannot go through. So not even oxygen and CO2. So if these lasts too long, you risk of starving. You risk of dying from hunger, from carbon hunger. In fact, it's called carbon starvation because you're not photosynthesizing anymore. So you're not producing the food, the sugar that you as a tree need to live. And this effect is much more evident in large trees. Because large trees have a lot of tissue to maintain, a lot of branches, a lot of leaves, a lot of wood. All these living cells need to respire, need breath to live. So actually, they use up carbon, just as we do, in order to have their metabolism. So if you're a large tree, you're using up every moment a lot of your carbon reserves just to stay alive. And this is why larger trees that have a larger diameter here on the x-axis, have a more severe growth reduction and a more severe mortality after drought episodes than smaller trees. And this effect can be significant. And there was a study, a very surprising study some time ago, showing that the Amazon forest is actually shortening down. So, of course, the trees are not shortening, but this effect, which is more evident in the southern part of the Amazon forest, the one that is more prone to periodic drought and deforestation, by the way, here, the taller trees are the ones that die first as a consequence of drought. And so if we lose the highest trees, the average or the top height of the forest as a whole will decrease. Satellite studies done by radar, as I was saying before, show us that in only 20 years, we have lost the topmost 3 or 4 meters of canopy, just due to the mortality that hits preferentially the larger trees, that, by the way, are also the most important, both in terms of carbon storage and in terms of biodiversity and habitat. But drought is not only a problem for grown-ups, it's also a problem for kids, for young trees, seedlings. This is a picture of Scots pine seedlings, experimentally subject to drought versus normally irrigated ones. And you can see the difference in development, both of the above ground part, but most importantly of the roots, of the root system. So the seedlings that were subject to experimental drought didn't have the chance to develop a well-formed root system. They have fewer roots, they have shorter roots, and so they are less and less able to suck up water and nutrients and to live where they have established. And this means that also the future forest is at danger of changing. In fact, this is the reasons why we say that forests move, forests migrate. Of course, the trees themselves do not move. What moves are the seeds. So if the seeds that are established on a given site don't find the right condition to germinate and grow, then the forest there has no future. And maybe it has a future somewhere else, further apart, maybe in a colder climate, because there the climate has become suitable and once was not. The effect, as I said, is that the forest as a whole will move. This is an excerpt from the Italian climate change adaptation that show us the potential impact of current climate change on the distribution of some important forest species. The red area is where the species are expected to disappear or to find conditions that are not conducive to growth of the new generation of trees. Just look on the right picture on beech, which is the most widespread forest species in Italy. The whole southern Italy is forecasted to lose beech, to lose conditions for beech growth. Of course, maybe some more species will come, more Mediterranean, hot and drought-adapted species will replace beech, but the landscape will change, and so the impacts of this can be both positive and negative, according to the function that we ask of the forest. This is the same dynamic, just projected at the European scale for broadleaf trees on the left and conifer trees on the right. The colors here express the difference in climate suitability in the future relative to current. So blue means that the area will be more suitable in the future, and red means that the area will be less suitable than it is now in the future. Just look at the conifer panel with all the red in Central Europe. This is exactly where we are having most trouble with European conifers. Huge mortality due to drought, due to insect attacks, bark beetle outbreaks, and we are losing conifers at a very fast rate in this area. Again, a lot of studies worldwide are dealing with this forest migration, forest movement stuff. This, of course, will happen also at the northern tree line. So species will have to respond to warming climate by moving northwards and possibly colonizing the tundra. So areas that are now treeless because of temperature limitation will probably become suitable for tree growth. And there are species that are expected to move north. But this is the theory. Reality might be different, because if you want to track the climate that's best for you, you have to be fast. Climate is changing very fast. And so the question is, are these species able to migrate as fast as climate is changing? And in most cases, the answer is no. The average speed of migration by trees, and possibly also by herbaceous plants, is slower than the speed at which climate will change, at least for the most severe climate change scenarios. So the horizontal line here represents the speed of climate change under different scenarios, and the bars are the studied rates of migration by several kinds of trees, vegetations, and animals. And as you see, trees actually cannot cope, so they can't move fast enough to track the climate as it changes. This is one of the reasons, and I believe I will answer to one of the questions that was asked before, why one of the actions that are being considered worldwide to meet this challenge is something called assisted migration. So if the trees cannot migrate fast enough, we can move them. We can move their seeds. Of course, we're not moving the trees, we move the seeds, and we can plant the seeds or plant the seedlings of a species much further north than where it is now, in the hope that the climate there will become suitable in the immediate future to ensure tree and forest growth and to be able to maintain this species and not losing it because in the home range, the climate will be not suitable anymore. This is already an operational measure in some parts of the world. In Canada, for example, in British Columbia, whenever a forest is harvested, new seeds are planted coming from much further south, 1,000 or 2,000 kilometers south of there. And we are in the process of starting experimenting also in Italy with some species like ABS, silver fir, especially in the Apennines. Preliminary results tell us that southern provenances, southern variants of the same species are much more adapted to drought and respond better to drought than the variants that are, for example, in the Alps or in the central Apennines. As I said, another important effect of climate change on forests is through sudden events. We call them forest disturbances. They can be wind or storm damage. It can be insect attacks. It can be fire. From all the data that we can muster, that we can gather, it really seems that these disturbances are increasing as a response to climate change. So not only their frequency, but also the amount of forest damage, here in million cubic meters of wood damage every year in Europe from this specific study. And both observations and forward-looking modeling tell us that this event will continue to increase at a forecasted rate of about 1 more million cubic meters damage every year. Of course, this means economic losses, but also means or can mean loss of ecosystem function, at least temporarily. So when a forest burns or when a forest is blown down by wind, of course, it's not lost forever, unless we are deforesting it. The forest will grow back, but it will take time. And this time will be a time where we lose the ecosystem function of the forest. We lose a part of carbon sink, we lose a part of slope protection, we lose water regulation, and so on. One of the most common talked about danger for the forest is fire. The dynamic of fire, the trend in forest fires globally is quite interesting. Because if you only look at globally burned area, so the surface that's burned every year by fires, we are still on a decreasing trend. So on average, so excluding extreme years, such as maybe 2019, on average, we're still doing a good job in firefighting. That is the reason why the globally burned area is still decreasing. But all models tell us that the danger of fire is increasing and will increase a lot due to climate change. And also the period of the year in which the danger of fire will be high, which is the length of the fire season. And large episodes of fire, such as in California, in Siberia, in Australia, or all the ones that we heard from the news, are already the symptoms that not the overall burn area, but the particularly large fires are already increasing. So we have an average trend of less burned area, but with more extremes, with higher peaks. And the extremes are the ones that are really worrying, because they are the ones that are responsible for more damage, more loss of life, more loss of property, and more damage to the ecosystem services. So the average trend doesn't tell the whole story. We have to look at these extremes, and those are already on the rise. What's also on the rise is the interaction between these disturbances, these agents of damage. In Italy, for example, we had this storm a couple of years ago, unprecedented damage to Italian forest, 40,000 hectares blown down in the northeast. And already in several regions, we are seeing insect attacks because the insect and the larvae of the insect feed on the dead wood that is now on the ground. We have seen at least 3 forest fires starting and spreading thanks to or caused by the dead wood that has been accumulated on the ground. So these facts can reinforce one another. And if we want to study their impacts, we have to remember also their interactions, their feedbacks. So what we are seeing is that climate change is acting on the forest via 2 different ways. Influences and effects on the productivity, so on the growth, on the carbon sink, as we were seeing before, and sudden effects on via forest disturbances. All these have the power to change the state of the forest today and tomorrow, and to change ecosystem functioning, to change the services of the forest, and in the end, change also the composition of the community. So what species are there, how they are growing, what diversity they can express, and so on. And there are parts of the world where these effects are already higher and more dangerous, both because the climate is becoming more unstable and more unpredictable, and or because the forests are becoming more vulnerable. So we always have to take these 2 factors into account: the danger and the hazard or danger and the vulnerability of the forest. It's the mix of the 2 that determines what forests of the world are bearing the strongest impact and the strongest risk from climate change. And you see the Mediterranean is one of the hotspots, South American forest, East Asian forest, but also Western American forest and Siberian forest due to the spread of forest fires. What to do? What can we do about it? Well, we mentioned sustainable forest management in the previous hour. It means that climate smart forestry is not only something that aims to maximize carbon sink, but also a forestry that tries to improve the resistance and the resilience of the forest to these kinds of events. Because saving carbon also means trying to prevent carbon losses due to forest fire, carbon losses due to wind damage, and so on. So some examples of techniques that are being part of climate smart forestry solutions worldwide. One is thinning. Thinning is thought to have a very significant effect on vulnerability to drought. In case of water shortage, there's no water available for all the trees in a forest. So some of them are certainly going to die. What we can do is remove some of them, harvest a part of the forest, in order to bring back the balance between the available water and the number of trees that are living there, in order to ensure that at least some of them can have enough water to drink, can perform their photosynthesis, and can continue their growth. Another very important aspect of climate smart forestry is how to prevent forest fires. So something called preventive silviculture. Preventive silviculture is carried out in many ways. What we have to prevent, as I said before, is the spread of the flame front. So we can actually, what we do is managing the fuels. So we see the vegetation, seeing the vegetation as the fire would see it with the eyes of the fire. So the trees, the dead wood, the vegetation become fuel. And what we want to prevent is the flame spreads both horizontally and vertically. So we have to act on the amount and on the spatial continuity of this fuel. We don't want to have continuous tracts of forest fuels, both horizontally and vertically. So, for example, we want to avoid that the flames can climb on the top of the trees and do more damage. So these are the principles of preventive silviculture, acting on fuel load and fuel continuity. Climate smart forestry also acts at the landscape scale. So we also have to assume a broader perspective on the landscape, because something that's very important for a forest in order to respond to these threats is diversity. Forests and landscapes that are more genetically and functionally diverse have more cards to play. If something happens to them or to a part of them, maybe there is another species, another community, another groups of species that can take over and ensure the continuation of the forest and its services. So diversity, not only at the forest scale, but at the landscape scale, is very, very important. But this diversity, genetic and functional, must be maintained, must be allowed to travel around. That's why at the landscape scale, the connectivity of forests and ecosystems is really important for them to be able to respond better to the challenge of climate change. So forests that are contiguous, that are not very much fragmented, they allow for more easy gene exchange, seed exchange, pollen travel, animal travel throughout the forest, throughout the habitats, as opposed to forest fragmentation, which is a very dangerous trend in many parts of the world. A fragmented forest is still a forest, but it completely loses all or most of its functionality because seeds cannot reach the forest anymore. The genes cannot be exchanged with external forests, so there can be genetic degradation of the gene pool, and we can lose adaptation traits, which are instead very important to be maintained. We don't know what parts of the genetic makeup of a forest is better suited to respond to climate. That's why we have to preserve the greatest diversity possible, so that we preserve in the process those parts of the DNA of the trees that will prove useful to respond to climate change. And this is done, again, by fighting forest fragmentation and ensure forest connectivity. And when a disturbance hits, when it happens, when we weren't able to prevent it or the conditions were too severe to prevent it, we must think very carefully about post-disturbance restoration. So this is a very special form of restoration that happens in forests or in ecosystems that have been disturbed. Usually, as I said, the forest is able to come back, but often we have to wait for a long time. Instead, in the case, for example, of a very severe forest, we have to wait from seeds from surviving trees very far away to reach the ground and germinate. So that can take several decades. And if in the process some drought happens, or heat wave, or a second disturbance, a second fire, then the regeneration, the natural regeneration power of the forest is put into real danger. So these are the situations when we can act with post-disturbance restoration. And there's a lot of research happening on how to better do this kind of restoration. For example, just one example, we are understanding more and more that dead wood, so the legacies, the leftover from the disturbance, can be really, really important and really strong in facilitating the growth of the new trees. That is not just a dead tree. It can provide a little shade. It can store a little soil upslope, a little more water and humidity. It can maybe prevent animals from eating or browsing or walking on the land. So it can be found to ensure the success of regeneration, both natural and planted. In fact, for example, in Switzerland, already in many places, they are experimenting forest plantations after fire in the vicinity of dead wood. So they're not removing all the dead wood, they're keeping some for this very special and very important function, and then planting the trees in the vicinity of the dead trees. So, wrapping up all that has been said, the relationship between forests and climate is twofold. They are a precious ally in mitigating the climate crisis, but they always bear and suffer the impact of the consequences of the climate crisis. What we want to do with the forests, obviously, and with land ecosystem, is to use them in order to mitigate climate change. They can't do everything by themselves. So this is one of the most recent papers that try to quantify the overall effects of all the management actions that we can do on climate mitigation. Again, you see, the overall sum is 11 billion tons of CO2, which is not nearly enough. It's less than 1/4 of all our carbon emissions now. There are more than 40 billion tons of CO2. But this 11 gigaton is very important, and we can and we must do something to attain it. The keywords are protect, manage, and restore. Protect the carbon sinks, not lose carbon, stopping deforestation. Protect the wetlands where carbon is stored for a long time in the soil. Protect the old growth forest, where carbon sink is not very fast, but the sheer amount of carbon that is already in the ecosystem cannot be lost. Manage. Improve the management of existing forests. Improve the carbon sink, taking into account the physiological limitations that we went through. Improve the management also of our agricultural and pastoral systems, which of course were not the subject of this lesson, but which can deliver very important carbon benefits. And then restore. Plant trees where it can have the greatest effect. Restore disturbed forest. Try to invert the deforestation trend to restore deforested ecosystems. The union of these three actions will be very important and will make a contribution to our necessary mitigation. Thank you.
Okay, Giorgio. Sorry. Thank you so much for your very interesting presentation. And again, if there are questions, now is the time to write or ask them. Please don't be shy.
I will soon appear in video as soon as my computer will.
And don't write them at the last minute. So Giorgio will have the time to answer them.
I cannot send them on words. We can open microphones, I guess.
Yeah. I have noticed that you put your contacts on the presentation, so in case they have to go in deep in some topics, they can contact you directly
in the chat.
Yeah, but the presentation you shared, it's already in the e-learning platform. So, but okay, you are free to write it again. So if they need more time to elaborate on the topic and on the data you provided, thank you in advance if you can answer them.
I don't know how many of the students that are listening have a forestry background, so I hope I wasn't too obvious in what I said, or too specific. I don't know. You will get feedback later on. Anyone that has a
I think Giorgio is freezing again. Can you hear me? This is Rosa Laura. Hi, Giorgio.
Hi, Laura.
I think most of the participants have a scientific background, mainly related to mountain development. There are a few foresters, and I think we share the CVs, yes, but most of them have a scientific background.
Okay. And
but
from what countries are they following?
I think we have about 22 countries represented, mainly, the main mountainous countries in the world. We have India, Nepal, Peru, Argentina, and a few African countries. I don't have the list in front of me. Armenia, I think. Danilo, help me.
Yeah, there's some participants from the Eastern Europe, and then Iran and Bhutan.
Yeah.
So, some Italian too. Yes.
Yes.
Yeah.
But I think during this is the IPROMO number 13, and I think during these 13 years we covered more than 70 countries around the world. And of course, our focus is mountains, so they are mainly mountainous countries. Usually, there is a wide participation from India, Nepal, Peru, Chile, Argentina, Ecuador, etc. And now we also have a few participants from Lesotho,
Hello?
Malawi, Kenya.
Interesting.
Yeah.
Well, I thank everyone from all the different countries for following, and I hope that health situations in these countries can improve or not become too hard. Oh, this is the list. Wow.
We have 21 countries represented.
Cool.
Okay.
Well, I wish you all the best for the conclusion of the course. I know that it's almost at the end.
Yeah.
This
is the last day, and there will be the last session this afternoon.
Good.
There is okay.
Thank you very much for having me.
Thanks a lot, Giorgio.
Thank you, Giorgio.
Thank you very much. And okay, we are going to conclude this first half of the session. So I'm opening the microphone so we can all clap our hands to Giorgio and say thanks to him. Thank you very much. And see you this afternoon at 4 p.m. Rome time zone for the second half of the lecture. Thank you again, Giorgio, and see you later.
Ciao, Giorgio. Grazie.
Bye.
Ciao.
Ciao, grazie.